Hi, good afternoon. Welcome to Epic Walkthrough Day. You will be looking at 4.4 and 4.5. And please make sure that you've taken a moment to look through 4.4 for words that you did not understand that made no sense when you read them. All right, let me have them. What words?
Conjecture.
Conjecture.
Yeah,
Oh, yeah.
Okay. That's how many times it shows up, conjecture. What else? That was it?
Using coordinate geometry.
Coordinate geometry. Okay.
Huh? You say it's your word.
Yeah. Which one?
The logical argument is that it's a man, right?
A logical argument. Okay, we'll describe a little bit more about what it is when we come back into it. Logical argument. Okay. Any others, or is page 1 clear? Thumbs up. Page 1 is clear. I've marked down everything that you've got as a question for when we come back. All right. Let's look at page 2. Read through the directions on page 2, and then read through the question really quick. Words or symbols that we have not already marked and don't make any sense. Give me a thumbs up if page 2 is clear for you. Thank you. All right, page 2 is clear. All right, let's look at page 3.
Flowchart.
Flowchart proof. Any other symbols or words? All right, let's look at page 3 real quick. Clear? All right, next page. Clear? Okay. Right now we're just collecting where I really have to hit, okay? We will go back and we will look through all of them. This one?
I think there are
Words or symbols? All the symbols make sense?
Oh, not the upside down.
The upside down T, okay. Which other one? That one? Okay. All right, this one. Clear? All right. Back page of this one. Any words in here that don't make sense? Baklava. Baklava? Baklava. Baklava. Baklava?
Sounds Jamaican.
Yeah, we're not sure. We'll figure it out. Okay, any others? Everything? Okay. All right, let's look through 4.5 then real quick. Words or symbols? First one, clear? Yeah? All right. Second one? Okay. Third one? All right. Look at the back page real quick. Oh my God, suddenly this class has turned into Star English 1. Don't worry, there's 3 answers for this one page. You don't have to fill it all in. Second page.
Well, I think I have to second page. You got second. There's another one over there.
Okay, there's another one there. That has the title. It looks like this. Okay. All right, so let's go back to 4.4 and let's start our walkthrough. Now that we know exactly where we need to stop and make sure that I've answered those questions, please make sure that I hit all of them. Here you go. Let's start with this word conjecture. A conjecture is a guess. I guess this is right. I don't know. But more than just a guess, this guess has got to be based on evidence, something that you see or hear or read. Okay, so it looks like in this question we're going to be making some sort of guess, and it's going to be based on some sort of evidence that we're going to either generate or see or read. Sorry, there you go. The next item that y'all had was logical argument. A logical argument is, you had mentioned, is it something like an if-then? It has a lot of if-then, yes. If this, look at all this setup that I did, I have all that. Then because I have all that, this is what is true, this is what supports my guess. Okay, so that's your logical argument. And you'll be building one. Yes, it's going to feel a lot like the proofs that you've been writing, but I'm not asking for a proof. I'm asking for a logical argument. So it doesn't actually have to end up being true at the end the way that a proof does. It just has to have the same sort of logical thought process. I'm basing this answer off of this thing that I saw. Okay? Coordinate geometry. Coordinate geometry is doing geometry on this coordinate grid thing. Where geometry is, hi, we're going to look at the relationships of shapes. You know, how does this triangle relate to this triangle, or to that square, or to this circle? We do the same thing, but we limit ourselves to this type of space, where then we have to use the rules of coordinates, the x, y axis, and distance formulas, and midpoint formulas, and slope formulas, and we have to be very numeric about it, as opposed to what we've been doing most of the time with just kind of talking about it in this abstract, well, it lives somewhere over here, and stuff, okay? So it becomes very kind of concrete and analytical, and you don't have as much room to move around. So that's coordinate geometry. Okay. Now that we've cleared up those, let's read this again. Can you do A? Can you do letter A? Graph triangles on the same coordinate plane. Yeah. Now look, I even gave you a coordinate plane. You have a lot of little ones, or one big one. What's the problem with this coordinate plane that I gave you?
It's not numbered. It has no origin.
Yeah, it's not numbered. There's no origin. But you can put it anywhere you want. Okay? She likes it in the center. And the question, the really kind of the big question on this is, where do I put the origin? Do I put it in the center, or do I put it somewhere else? Where's a good place for it? Well, a good place is anywhere that's not a bad place, is the short answer. So let's look here. These are all positives, so I don't really want to put it way up here, because then I have nowhere to go. I've got some negatives here, so I don't want it way down here, because then again, I've got nowhere to go on the negatives. So the center, as she was suggesting, seems to be a really good spot for it. So drop those axes there in the center. I'll do that with you.
Good job.
Try to make your axes a little straighter than I did, because I clearly cannot draw straight lines. I know. That's why this is my messy copy, and you have a nice, neat copy that you can make it in. All right. B. Use the graph. Okay, you've already drawn them. We're going to pretend you have. You haven't, but pretend you have. So you've drawn them somewhere, and you're going to use that drawing to make a conjecture, make a guess as to whether or not you think these triangles are congruent. In order for them to be congruent, what needs to be true? What does congruent mean? Same size, same shape. So when you draw these things, if you get two things that are different shapes, like one of them is a triangle and the other is like, I don't know, a rectangle, your conjecture is, no, they're not congruent. Why?
Because they don't have the same size.
Because they're not the same shape. One's a triangle, one's a rectangle. Okay, they may be the same size. We don't know. All we know is that they're not the same shape. That's the first thing you say. You could probably put an argument in there that they're not the same size either, right? You count the little boxes inside. Yeah, totally valid argument too. But the easiest one to state if one's a triangle, one's a rectangle is they're not the same shape. Okay? But they also need the same size. So if you draw them and one is really big and one is really small, again, your conjecture is no, because they're different sizes. Okay? So you can't get this conjecture wrong unless your conjecture has absolutely nothing to do with the question. Like if you go, hi, my conjecture is purple. What? Okay? So it's a yes or no, and then tell me why you thought they were congruent or not. Logical argument. Using coordinate geometry, which means you're stuck using distance formula, midpoint formula, slope formula. You can pull in the reflections, the transformations in the coordinate geometry. You remember all of those guys? The translations and reflections and this stuff. You can, because this is coordinate geometry. See, rotations on the coordinate plane. You're talking about the relationship between this shape, and you're on a coordinate grid. You can totally bust this out if you find some sort of relationship that matches these. I've given you a hint of one of the easiest ones I think you can use, though, which is distance formula. It's easy in that there's not a lot of hard thinking to be done. You're just comparing numbers. But it's time consuming in that there's a lot of work to be done. Look at your postulates and theorems and stuff from yesterday. Because in coordinate geometry, it's a lot more challenging to find information about angles than it is to find about side lengths. Do you have in here any kind of relationship or any kind of postulate that deals with just side information? The side postulate, the very first one. The side postulate says that if the three sides of one triangle are congruent to the three sides of another triangle, then they're congruent, which is what you're trying to show, that these are congruent, yes? Which means if the distances of these corresponding sides are equal to each other, those corresponding sides are congruent. Make sense? If I take this triangle JKL and I look at this side between J and K, I find its distance. And then I look at this triangle and the same letters in the same order, the first two, NP. If I look at the distance between those points, they have the same distance. Those sides are the same size, which means they're congruent. Repeat for all the other two sides of the triangles, and if everything is all the same, then those triangles are congruent because of side, side, side. That's your logical argument. We just talked through it. And so you showing the rest of your logical argument here is you running through the distance formula the 6 times you have to do it, paying really careful attention that you are doing the corresponding sides, and then stating whether or not these triangles are congruent or not, based off of your conjecture. So you're going to either support it, yes, look, I was right, I said they were congruent, and I showed that they were. Or, all right, I said that they were congruent, but if you look at my work, they ended up not being congruent.
So it's almost like a hypothesis?
Yep. It's your hypothesis, and this is your scientific test that you're running through. Okay? Does it say anywhere here that you are not allowed to use decimal form for your distance? Guess what? You can. It's all good, which means bust out the calculators, write just enough work so that you know what you're substituting and you can make sure that you type it right in the calculator, push enter, and write that number down so you can do your comparisons. Okay? Decimal, totally okay on this one. Feeling good on this first page? Feeling like you can get started on it? Okay, don't forget we have work day tomorrow, so if when you're starting on it you run into a wall and you get stuck, ask someone tomorrow, okay? All right, let's look at number 2. Read it again. The same or different from the first one? Different. Very different or a little different? A little bit. What's different? No graph. Doesn't have any graphing. All right, so you don't have to graph this one. Whew, thank goodness. What else is different? You cannot use decimal form. This is the exact same problem, different numbers, but now no decimal form. And so I'm going to remind you that you can find information in your notes sections C0L9 and C1L2 on how to handle the distance formula to get it down into radical form without going to decimals. So this is again reinforcing that concept of dealing with the radicals, which is going to be big for you guys when you hit Algebra 2 next year. I want you to have some comfort in dealing with them, okay? So you can go there for help on getting that simplification done. Okay? So second page looks pretty good. Feeling okay with it? Other than the, oh my god, I have to simplify and deal with radicals. But knowing what to do, at least we're feeling okay. All right. Let's look at this one. The flowchart proof was the big concern for you guys. What is a flowchart proof? We've never seen one of those ever. You have, yeah, you have. Actually, you've done a whole bunch with me already. I just never called them flowchart proof because I'm spoiled. No, I don't know why I didn't call them flowchart proof, but this is, I don't know. That's a flowchart proof. That one. So you got to write something like this
Oh,
for this proof.
awesome. Great.
And once you're done writing the flowchart, you got to turn it into the 2-column proof. Again, which we've done. So let's go ahead and let's set this up. Let's do this flowchart proof together to remind us, because I know that these proofs, especially the flowcharts, are still like, oh my God, I can't. Let's do it together. I love starting with a starting location. I like start reading to the left, and I right to left, and then I like starting at the top and reading my way down. So I like putting my starting point on the upper left-hand side, and so I'm going to take the given, and I'm literally just going to rewrite it. There is a typo in the given. We'll find it here in a minute, and we'll fix it. All right, so there's the given. Just going to put that in thought bubbles. And then my prove, where I want to end up, I'm going to put way down here on the lower right-hand side of my workspace. And I'm going to put it in a big shout box because I'm done and I'm very excited about that. All right. We're going to use the given to make sure that our diagram is all up to spec and is working okay, and that it makes sense. So segment PR right here is congruent to segment DE. Segment PT right here with the 2 little bars is congruent to segment DE. Which one is it supposed to be congruent to? Yeah, DF. There's our typo. So we're going to go ahead and just change that. I acknowledge and admit that that was a typo. And the E's and F's look so much alike that I was like, I didn't even see it. Angle R and angle E are congruent. Angle T and angle F are congruent. All right, so we have all the given. And so now the question is, do I have any postulates or theorems from yesterday that use this information that I could possibly leverage to get me to where I want to be, saying that triangles are congruent? Look back at your postulates and theorems from yesterday. Side angle side? Huh? Looking for anything that could possibly get us from these markings to the triangles being congruent. Now she had said side angle side. If we're using side angle side, remember that that means that the angle needs to be included between the sides. It has to be sandwiched between them. So if I have these 2 sides here, my included angle is this one. You're not wrong. You can totally use side angle side to prove that these triangles are congruent. However, you first have to go in and show that those angles that I marked with dots are congruent to each other. It is something you were able to do. You may have to go further back in your book and try to find a different theorem or a different postulate that'll get you there. But you can do it. Side, side, side. Again, I'm missing this 3rd side right here. I'm not saying you're wrong. I'm saying you could totally do it, but you have to prove those sides are congruent first. Hypotenuse leg. In order to use hypotenuse leg, I have to have a right triangle. I don't have it marked, so unless I find a way to show that one of these angles here is 90, I'm not allowed to use it. And again, not saying that you're wrong. You totally could, but you've got to find a way to do that first. And right now what we're looking for is the easiest path. We're running into 3 different options that we're missing some information for each one. Side, we had already mentioned. We're missing this 3rd side. Angle, side. She said I have angles and then a non-included side. And I have enough information already. So because I have enough information with angle, side, I can connect them immediately with angle, side. And this proof, this flowchart, is just that. Do you remember how to go from here to a 2-column proof? Or do you want that walkthrough real quick? Walkthrough? All right. Let's do the walkthrough. In a 2-column proof, the left-hand side is always the statements and the right-hand side is always the reasons. So I left them blank for you to label them so that you can start really internalizing that the left is statements and the right is reasons. In the 2-column proof, the first reason is always given. In a flowchart proof, the statements are always inside the shapes that you draw, and the reasons are always on the outside. And usually on the path from one to another that tells you what you're moving through. Okay? So my first reason here is given, and it's next to this box, so all of this stuff is the statement for given. So we're just going to rewrite all of this. You can consider your flowchart almost like a rough draft. If you were in your English class, that would be like your brainstorming moment. And this 2-column proof, if you were in your English class, is going to feel and look a lot like an outline. I like using a different color pen to put a check mark inside the things that I've already done. So I keep a real kind of visual look of what I've done, and I know what I've already cleared out. My recommendation in the 2-column proof is to put a very faint line or dotted line between each statement and each reason pack, so that way they stay all together. Okay? I'm now outside the shapes and I'm following a line, and so this is my next reason. I am moving through angle, angle, side. Was it a postulate or a theorem?
Theorem.
Angle over side is a theorem.
It's a theorem?
It's a postulate.
Angle, angle, side.
Angle over side.
Angle, angle, side.
Theorem.
Theorem? Your note says postulate? Or is this postulate?
Yeah.
Yeah? Okay, so we've got theorem, 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 theorem. Okay, so I think maybe just miscopy, adjust, change your notes. No big deal. Happens to me all the time. I'm still in college, so it happens to me all the time. It's okay. All right. And what's the statement we end up after we go through angle, angle, side? Triangle, blah, blah, blah. We don't write the actual theorem. Okay? We are going to write the statement is the thing in the box.
Triangle PRT is congruent to triangle DEF.
Exactly. Do you see it? Okay. I've written this reason. I've written this statement. I've completely run out of stuff to write. I'm done.
This is the easiest proof.
Yeah.
No, they get a little more complicated as you go, but certainly the ones I handed you before Christmas, that pack of 9, were the most complicated and hardest ones. So if you got even halfway into and then got really confused, you were able then to get through these. And so that was the point, was here, frustrate yourself on these. Just try to get a little bit of success on these, and that way these are like, oh man, I got this. You can go back to them and be like, I can do this. Okay? All right, I want to take my 5 seconds now to show you how to do this last page on 4-5. Yeah. This last page on 4-5 asks you to take a 2-column proof that you've already written, well, the 3 that are in this packet, and turn them each to a paragraph proof. Here's the lazy man's way to do this. Are you ready? Literally, this is going to take 5 seconds. I'm going to turn this 2-column proof into a paragraph proof in 5 seconds. Are you ready? Sentence number 1. You write all the stuff in the number 1 statements box. You just blah, 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 blah. Don't actually write this one because you're going to write the paragraphs for these. Okay? But this is how you do it. You take all of this stuff and you write it. And then you write the word because, and then you write all the stuff in the reasons box. Period. Next sentence. You write all that stuff. And then you write the word because, then you write all that stuff. Period.
So like kind of like really short sentences.
Yeah, those are the shortest sentences. That's like bare bones, I will take it. Y'all are pre-AP, and so I want to challenge you to try to make it a little more. So start it off like that. It's perfectly acceptable. And then go back and put your English writing teacher hat on, thank you, and be like, how could I make this sound better? Because having the word because in every single sentence is totally repetitive. And who's your English teacher? King? How badly would she hurt you if you turned in a paper like that?
I didn't care.
Right. Either she wouldn't care, zero, I don't care, or she'll gripe and freak out, right?
No.
So then go in and find some other transitions. Okay? But that's it. That's all right. Cool. All right. Let's look at the next one. All right. We're 4-4 again. Look at 4-4. What do we have?
I think that's a side-side postulate.
She's saying it's a side-side-side postulate. What do you think? You agree? You disagree?
Yeah,
You agree? Why do you agree?
because it has all two sides there.
All right. Enough information. You go through side, side, side. Done. Proved. Next one.
Is this one of the new ones?
These are just, we're still kind of in that same section. What do you mean one of the new ones?
The
It's
postulate.
gonna-
Side postulate.
Side, angle, side. She wants to go through side, angle, side. Remember that for that side, angle, side, you have to make sure that that included angle is congruent. Now, you're not wrong, okay? It is totally possible on this one to go side, angle, side. Side, angle, side. But in order to do that, you would have to first somehow prove or show that those angles are congruent to each other. If you could find a way to show that those angles are congruent to each other, you can definitely use side, angle, side. Is there a faster way to get there than that? Is there a theorem to show that those angles are congruent to each other? Not that we've run into yet. There will be, but we're not in that section yet. Give me 2 more units.
Wait, it's not angle.
Angle side.
Angle, side, angle. Angle, side, angle. Again, we would need to grab like this angle and this angle and show that both of those angles are congruent. Again, one of those, we're not there yet, moments. Leg, leg requires that there be a right triangle. Unless you have some way to show that one of those corner angles are right angles, we can't use any of the right triangle theorems. We don't have right angles, right triangles. Angle, angle, side, again, we'd have to get 2 of those angles. You're not wrong, okay? I'm not saying that to say, no, you're wrong, you picked the wrong theorem. But you're missing information. And if you could get that information, then yes, you could use those. And so the main question is there a different theorem or postulate that you could do without having to use so much missing information? In this case, 2 angles. The side, angle, side, that was the first, the red dots, that was the first.
Included side.
Angle, angle, side?
No, included side.
Included side. Included side is a concept more than a postulate theorem. You're not sure what an included side is?
No, I know.
Oh, okay. What information do you have?
That those sides are equal.
Those sides are congruent. So you got 2 sides of these triangles, which means really you're already set up to use either side, 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 because all you're missing is one side, or side, angle, side, because all you're missing is one angle. That has the least amount of missing information, right? So looking at side, angle, side, we already had that conversation. We'd have to somehow show that those angles are congruent. And I'm going to tell you right now that yes, there is a theorem that says that, and yes, we will have it at our disposal, but we don't have it yet. It's coming up when we do 4-sided figures. It's 2 more units from now. So we can't use it yet. So let's look at side, side, side. If we wanted to use side, side, side to go from the given to our prove line, our end, what extra information do we need first? The third side. Where's the third side of that triangle that's not marked congruent? In the middle. This one. Yeah, this ST. So we need to somehow say that line segment ST is congruent to line segment ST. What's the name of that property that allows us to say a thing is congruent to itself? Yeah, flip back. Flip back. From where we are in our notes, flip back like
Wait, say it again?
2 pages. What is the name of the property that allows us to say a thing is congruent to itself? Under the congruence, properties of congruence.
Corresponding?
There you go. You've gone a little too far. Those are transversals.
Reflective changes, those are proofs.
Okay?
Reflexive property?
Yeah, the reflexive property. The reflexive property of congruence is the one that says, hey, when you got a thing, it's always congruent to itself, dude. I need you to be very picky here because I will be very picky here.
Can we actually draw that?
Yeah. It must be the reflexive property of congruence. And I'm being very particular because there's also a reflexive property of equality. These are not equal signs, these are congruence signs. So you must say of congruence. Otherwise, I don't know which one you're talking about. Okay? You can turn this into a 2-column proof, no problem? Yeah? Start with the statement, start here. Blah, blah, blah. Okay, I can't go any further until I get this one in. Blah, blah, blah. Now I can use that one, and I can go to them. Okay? All right. Let's look at the next one. Now on this one, we were asked to look at what this upside down T symbol thing meant. It is the symbol for perpendicular. What does perpendicular mean? Yeah. Yeah, perfect plus makes a right angle, 90 degrees intersection. So this means that line segment NP intersects line segment PL at 90-degree angles. And so we have the reason for those little box marks there. And I'm going to go ahead and help you with some of these symbols because I realize that this is just way too small. That's an N, the middle one is the P, the bottom one is the M, and the L is all by himself. Poor babesy. A loner for life. Because he's an L. He's a loner. All right. What do we have?
Numbers.
Yeah, I agree with you.
No,
And we have letters. We've got triangles. They're right triangles. 2 right triangles, which means on top of your normal triangle congruence theorems, you're also allowed to use any of the right triangle congruence
Why
theorems.
is there a line on PM?
Why is there a line on PM? Probably because it's congruent to something.
What does that mean?
I don't know. Look at your
Just
given.
right across from it. 'Cause you're right.
We should find out.
Yeah, look at the given.
I bet it's
You're in the right
in
hand. How do you know it's NP? Because the distances are equal. So the given,
Is that a mistake again?
no, it's not a mistake. The given allows us to say that NP is, line segment NP is congruent to line segment PM because the distances are equal. What's the name of that you're telling me?
What? Are they equal?
That the distances are equal allows us to say it's congruent. Is that a definition, a postulate, a theorem?
Side. Wait, never mind.
We're looking for how to explain how we went from the distance between NP is equal to the distance between PM
Like that.
to those 2 segments are congruent.
Theorem.
Transitive? It's a definition, actually.
Oh, it is.
Yeah, but of what? What are we defining?
It's like a property.
It's similar to a property. It's actually formally a definition. But the question is what terms definition allows us to say that because the sizes of things are the same, those things are congruent? You're giving me the names of postulates. This is a definition. Later. What's the definition of congruence? Same size. Same shape. So the definition of congruence allows us to go from the sizes are the same to the things are congruent. All right. Now we have that these two things are congruent. Now what? What theorem do you want to use to get to the end, that the triangles are congruent? It's a right triangle, so if you want to look at the right triangle theorems, go ahead. You have a leg right now. Leg angle? Okay, if you want to use leg angle, you have to show that one of these other angles, one of these other cute angles here, are congruent to each other.
So would it be leg,
Leg, hypotenuse, leg. Let's talk hypotenuse, leg really quick. We would have to show that the hypotenuses are congruent. Hypotenuse, I don't know yet. I haven't figured it out yet. Now, I'm not saying that you can't. I'm just saying it looks challenging. You had suggested leg. I have one leg. I just have to find the other. In this one. How do I say that this leg PL is congruent to this leg PL?
The reflexive.
Yeah, the reflexive property again. Yeah, so I can pull in the reflexive property of congruence. I'm abbreviating again. To show that PL is congruent to PL. And that, together with this statement over here, can allow us to get to leg. Wait.
What?
We're missing something on leg, aren't we? In order to use leg, what kind of triangle do we have to have? And we do have a right triangle, don't we? But look at our flow chart. Do we have anywhere in our flow chart saying right triangle? Then we have to have it.
90 degrees.
Yeah, we've got to be able to say that this triangle right here and this triangle right here are right triangles. What allows me to say that? There's a perpendicular, which creates that 90-degree angle, and the definition of right triangle says, yeah, the definition of right triangle says, if you have a right angle in there, it's a right triangle. So from the given definition of right triangle tells us that we have right triangles, which then, connected with these other two, allow us to go through leg, and to where we want to be. This one, a lot more complicated than the others. Just because there was some missing information that we had to state really clearly. Feeling a little better?
Is this what we look forward to in college?
I'm sorry, one more time?
Is this what we look forward to in college geometry?
Yeah, if you're taking a geometry class in college, this, except depending on the professor, you're either going to go way more in depth and kind of go edge of known geometry in Euclidean space, or if you had a professor like mine, they take you out of flat paper and into the floppy paper. And you have to do all of this, but on floppy paper, which is way harder because the rules are all different.
My brain's hurt.
Yeah, I know. Hurt my brain too. This explains why I'm like this. All right, feeling better? Better? Okay. Let's look at this one. I'm going to check my time. We're doing okay. All right, let's look at this one. We have our given. We know that these things are midpoints. But what does this midpoint tell us? What's the definition of midpoint?
Meet the center.
It meets at the center. So V, and that's the code, in case you need to go back and look at midpoint again. That's the lesson code. So V is in the middle of Y and Z. So what does that mean for this segment and this segment?
They're congruent.
Interesting.
Yeah, they're congruent. So the definition of midpoint is going to give us that these line segments are congruent to each other. Are those the only line segments that the definition gives us as congruent?
No.
Which other ones?
It's in W.
There you go. All right, so you know you can write the second one in there. I won't do it, but you know that it's there. All right, I've got two sides, which means I can use this information with something else maybe, because remember I need three things, so I'm missing something, to get me to where I want to go. What am I missing? I can either go side, 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 or side, angle, side. If I go side, 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 I somehow have to show that these sides are congruent to each other. And right now, it doesn't look like I have any way to do that.
You get the angle.
I could look at this angle that's right in here. What's the relationship between those angles? Recall code. Chapter 1, Lesson 5, Angle Relationships. She had said vertical angles. Double check. You're right. You opened it up, you saw it. What do we know about vertical angles? They are congruent. What was the name of that theorem again? I heard it. Vertical. Yeah, the vertical angle theorem. So I have to say first that they are vertical angles. And I can pull that by the definition. And from the definition of vertical angles, I can use the vertical angle theorem to give me that those angles are congruent to each other. So the definition of vertical angles tells me that those angles are vertical. And then the vertical angle theorem tells me that they're congruent to each other. I can then use this angle and these two sides all congruent to go through side angle side postulate to where I want to go. Got it? All right. I'll leave this here a couple more seconds, then we'll go on to the very last page. Yeah. Oh, here? The WV. Yeah. Okay. We only have a few more minutes to the bell, and I want to get through this one. At the very least, I want to define this word, baklava. So if you have your phone, please go to your very favorite search engine. Thank you. Mine is Google. Let me turn down the brightness. Siri, what is baklava? Please don't tell me it's when my Minecraft buddies come up behind me and pour lava on my back. That would be not happy.
Minecraft cheats.
I was trying to look up chess, okay? I wanted to see what the chess looked like because I was making a gift for a friend.
And autocorrect.
I don't think that's
And here's the reason. I'm mispronouncing it. It's not pronounced baklava. It's pronounced baklava. Baklava. I think it's Russian.
But it's spelled right.
Yeah, they spelled it right. Good.
They spelled it right.
Okay, this is what it is. It's a pastry. It's a pastry. That means it's some sort of baked good, like a cake. Oh my
God.
Oh, look at that. Chocolate and nuts and deliciousness. It's from Turkey? Okay.
Yeah.
It looks like a dessert lasagna. Check that out. Oh my God. All right, so Sonia, this girl Sonia made baklava, and she didn't give us any. Thank you very much. See you tomorrow.